Hello class. So today our lecture is about non-random solutions. So we saw that randomization is kind of the gold standard of impact evaluation, but you don't always have that. And so what are the other solutions you might have with non-random data? These are the packages that I used for these slides. So before we go into the non-random solutions, let us talk a little bit more about randomization and talk about how you test for whether your randomization worked the way you were hoping for it to work. So randomization can go wrong too, right? Imagine you might have drawn samples at random, but they actually are in fact different. For instance, you may have a flawed or a bad sampling frame to begin with, or your randomization procedures might not be of very good quality, and you might have actually done some bad randomization. Or you could just have sheer bad luck. So you could have a treatment and a control group that are different, even though you drew them from populations that were not different. So that's what we typically call a type 1 error. And so when we do our empirical work, we like to check for that with what we call a balance test. So what are balance tests? Well, in the ideal situation, you have some pre-treatment data, and so you can check that variables between your treatment and your control group don't differ. So you could check that there is no statistical difference in the y before, in the pre-treatment y variable. And you can also check that there is no statistical difference in all the relevant x covariates before. So we often call that pre-treatment balance tests. Now, in some situations, you don't actually have pre-treatment data, but even if you only have post-treatment data, you could do balance tests, for instance, on the time invariance characteristics, right? Some of the x's don't vary with time, and you can check that on those x's, your treatment and your control groups are similar. In practice, what do balance tests look like? Most of the time, they look like tables like this. You'll have a column for the control, a column for the treatment, and then a column that shows that the means on all of these different variables that matter to your analysis, that the means are not different, are not statistically different. So the goal is to show there's no statistical difference between your two groups on a whole variety of measures. You can also run some visual balance tests. In that case, you might try to look at the distributions and see that the distribution of your y variable, for instance, is the same between the two groups. So here is some code that does that with the fast food employment data that you worked with in your homework from the Carden-Kruger paper that you're familiar with. So with this command, we're going to make a density plot that visualizes the balance of the employment variable, the pre-treatment employment variable. What you see that although the distributions are not exactly the same, they're quite similar. There's a lot of overlap. So this would be this would qualify as a pretty decent balance test. Distributions are quite similar. It is important to know that balance tests are a little bit controversial. Not everyone agrees that balance tests are the best thing you can do, even though they're very commonly used. So one argument against the balance test is that if you did randomize, then the assignment is random and you should not be testing that. If you used a proper randomized procedure, then you should not be testing for the balance, because in that case, the samples are random by definition. The second argument is that if you check balance on all of your variables, then clearly some of them will fail, and actually by definition, 5% will fail your 95% confidence test. So in that sense, you check 20 variables, one of them will not balance, and you might make wrong decisions based on that. And finally, the last argument is that just because you can check that all of your control variables are balanced, it does not mean that your y variable is balanced. In other words, the balance test is trying to see whether your two groups had similar patterns in their y variable before the treatment. And just because you checked a bunch of other variables and found balance, that doesn't say anything about whether the y is balanced. So if you want to know more about these arguments, there's a really good paper here by Mutz et al. That explain everything, and here there's also a World Bank blog that explains a lot of this. Okay, and so in spite of all of this discussion and controversies about balance tests, I still wanted to tell you about those because Most of the controversy is about whether or not you should do balance tests when you have randomized data, but most of the time you don't actually have randomized data. And balance tests in general as a concept are still useful, for instance, in matching methods, and therefore you should be aware of what balance tests are and how to do them. So that brings us to the meat of this lecture, which is what do you do when you don't have randomized data? Well, if your data is not random, you need some other identification strategy. So again, identification strategy means a source of plausibly exogenous data variation, which can be considered as good as random. And so today I want to talk to you about 4 common identification strategies, 4 common solutions for when your data is not perfect. And those are instrumental variables, natural experiments, regression discontinuity, and propensity score matching.
Okay, for this part I'm going to try a different mic, see if I can get the sound to be a little better than in the first part of the lecture. Please let me know if one way is significantly better than the other way. Alright, so instrumental variables. You know a lot about those already, so we're going to go fairly quickly over them, but I want to make sure that I hit a few points. So in short, instrumental variables are when you use an exogenous z variable to instrument, quote unquote, for an endogenous x variable. So you have z that affects x that affects y. But the relationship between x and y is fraught with endogeneity, and so you use z as an instrument for x. And so the regression you run in those cases is in essence split into 2 sub-equations. You have what you call the first stage, which is where z determines x, and then the second stage where x determines y. If you're not familiar with this framework, or if you've forgotten everything you've learned about it, just check on Wikipedia and other sources that are easy to find. Now, if you remember from those classes, the key issue with IV is always the exclusion restriction, what we call the exclusion restriction. So IV essentially relies on 2 assumptions. Sometimes those are framed as 4 assumptions, but let's just go to the simplest. 1 is the relevance and 2 is the exclusion. The relevance is that Z is actually associated with X. So most of the time we like to think of Z as determining X, but actually correlation is fine. The second big assumption is the exclusion restriction, which means that Z does not affect Y in any other way than through X. Why is that called the exclusion restriction? Well, because it says you can exclude Z from your model of the causal impact. Now, the second assumption, the exclusion restriction, is by far the bigger problem. Why? Because you cannot really test for it. And so, for instance, you'll notice in the seminars, virtually any time somebody comes up with an identification strategy, there's somebody in the audience that will ask a question about the exclusion restriction, or will say something about they don't believe that the exclusion restriction is satisfied. Okay, let's use some graphs to explain IV and the exclusion restriction. So here we're going to use something that people recently have started calling DAGs, or directed acyclic graphs. DAGs are actually very useful in mathematics, they're useful in graph theory. In economics, people have decided to use the term, although I would argue that most people only use it as excessive jargon when they're trying to impress people. And actually, oftentimes they use it improperly when they have a graph with arrows without checking whether it is a directed and acyclic graph. But that being said, you should know what a DAG is, because nowadays it's a common term that is used. And definitely try not to misuse the concept. And so in any case, here is a DAG, here is a graph for how we explain IV. And we've been using this plot to explain IV long before any economist had ever heard the term DAG. So here is your problem, your X. So here's the problem, your X determines Y, but there is an unobserved U variable which explains both of them, and so you have bias. However, you have this other variable Z which affects X, which you can use to instrument for X. Now, U is the unobserved confounder. It is the reason why you need an IV. And so what is a good Z? Well, first of all, Z has to be exogenous to this system. That's what this cross says. Then 2, Z has to be relevant. That's what this arrow says. Z is associated with X, but most importantly, the exclusion restriction is this red cross. Z cannot be affecting Y other than through X. That is all I want to tell you about IVs, because I know you've already learned a lot about this. You've learned about the econometrics behind it. You've learned about the matrix algebra behind it. But I just wanted to say that from an applied perspective, what is exactly what you are really focusing on and what you should think about when you're contemplating the use of an IV. The most important problem is this exclusion restriction. If you have doubts over the validity of your exclusion restriction, that is going to really complicate your use of the IV.
Okay, so part 3, a natural experiment. As you see, I am again trying new gear. Let's see how this works out. So natural experiments are some of economists' favorite way of trying to look at causality, and they make for some of the most interesting and some of the cleverest identification strategies that you see in the literature. So what is a natural experiment? Well, a natural experiment is just an event that defines two groups, the treated and the control. And this event is out of the researcher's control, which is why it is natural. And people will find themselves in the treated or in the control groups essentially at random, which is why it's an experiment. So you can think of something like a natural disaster. So clearly it is exogenous. We don't really have any impact, any direct impact on many natural disasters. Some of them we influence, but mostly we don't. And those who get treated by the disaster event are essentially randomly assigned. Even though there are areas of the world that are more prone to natural disasters, nobody really knows or can predict where and when it is going to strike precisely. So the most obvious good examples of natural experiments are natural events such as tsunamis or earthquakes. But very often we call human events that feel exogenous, we also call those natural experiments. So for instance, a change in the law or a change in the policy that is essentially exogenous to the people that are affected by the law or the policy, we tend to call that a natural experiment as well. Sometimes people will call that a quasi-experiment, although that term is also used a little bit differently. Sometimes people just say quasi-experiment when they have an experiment that doesn't have proper randomization. So these two terms overlap quite a bit. How do you analyze data from a natural experiment? Well, in essence, you treat it as if it came from an RCT. The logic is that this is like an RCT that happened by accident. So very often, data from natural experiments will be analyzed with difference in difference specifications. Either the clear before, after difference in difference, or what is sometimes called continuous difference in difference, which is when your treatment is a continuous variable, like the intensity of an earthquake rather than the occurrence of an earthquake. So you've already worked with an example of a natural experiment in your homework. You've worked with a Carden-Kruger minimum wage paper. In that case, you can think of the minimum wage as a natural experiment, or a quasi-experiment, some would say. So of course, in a case like this, the treated people are the ones in New Jersey, the non-treated people are the ones in Pennsylvania. You could say that there's an element of randomness in terms of who gets treated and who does not, but you could also argue that New Jersey and Pennsylvania are not exactly the same, and people don't randomly locate to New Jersey and Pennsylvania. So obviously, you have to control for the fact that this was not perfect randomness. And that is why these types of approaches really tend to need panel data, because you really want to control at least for those time invariant unobservables that might be driving the non-random aspects of this experiment. Okay, so next up are regression discontinuity. Again, regression discontinuity designs are some of our favorite identification strategies as economists, and they have led to some very exciting papers. So what is the intuition behind regression discontinuity? So imagine that you have a treatment that in itself is not randomly assigned. However, there is some rule, some arbitrary rule that decides who gets treated and who doesn't. So to take a very recent example, the COVID-19 relief checks. People with incomes below 100,000 get them, and people with incomes above 100,000 do not get them. It's a clear rule. Now, let's say we might want to find out the impact of getting that check on some outcome. Let's say maybe indebtedness. So following with this example, people with incomes below 100K get them. But the important thing is that this cutoff can seem arbitrary. At least from the point of view of recipients, that's as if it was random, because the government could have set it at 80,000 or at 123,000 or really anything it might have wanted. Of course, the cutoff point was not decided randomly. They didn't just throw a die to decide what the cutoff point would be. But it is arbitrary in the sense that it could have been any number, as far as we're concerned, within a certain range that makes sense. Now, the key to regression discontinuity is that we're going to compare people who fell right below that threshold to those who fell right above that threshold. The idea is that arguably those are quite similar people because their income differs very little. However, it puts them on one side or on the other side of this arbitrary dividing line. So formally, mathematically, how do we express this? Well, we say that the treatment depends on an assignment variable. So we still have our treatment dummy, the I, but this time it depends on the value of an assignment variable, x. Now be careful, in this case, x is not just our covariates, it's the assignment variable. So we say that the treatment is received depending on the value of x relative to a cutoff point x0. And so d is equal to 0, you don't get the treatment if your x is less than x0, and it's equal to 1, you do get the treatment if your x is greater or equal to x0. There is a key assumption behind that, and that key assumption is that people cannot manipulate their x. There is no self-selection because you want to be a part of the treatment group or not. And by the way, this assumption doesn't entirely work for the case of the COVID-19 checks because they are decided by your 2019 income on your tax return, or if you did not file it yet, the 2018 income on your tax return from last year. And so you can manipulate a little bit by delaying the time that you're going to file this year's tax return. However, there are some papers that show that even in that case, you can get an identified impact. Now, importantly, regression discontinuity really narrows the focus to the people around the cutoff value. So you are not just comparing the whole group of people who are below the cutoff value and the whole group of people who are above the cutoff value, right? Because those groups would not be comparable. If you just compare Americans that make less than 100K to Americans that make more than 100K, clearly on average, these are not similar populations. And so it really would not make any sense to just compare the expected value for the treated to the expected value of the non-treated. Rather, what you do is compare what happens around the cutoff value. How do you do that? Well, what you're aiming for is something like this. You estimate the relationship between the assignment variable and the outcome variable, the relationship between x and y, on either side of the cutoff value. The cutoff value being this red line right here. And so what you want to estimate is this jump. So you get a regression line like this below the cutoff, a regression line like that above the cutoff, and this is the regression discontinuity. Now notice that this is just a shift of the intercept. The slope with respect to x, the assignment variable, is the same on both sides of the discontinuity. This is the same beta that only this jump shifts your intercept.
Okay, so what is the typical regression discontinuous regression? Well, all you need to do is add that dummy as a shifter. So you let di shift the relationship between x and y. Again, x in this case is your assignment variable. It's not just any control variable. So you regress y on alpha beta x plus rho d. And in this case, this rho captures the shift. And of course, you could still add covariates to this. So how do you interpret this rho? How do you interpret the regression discontinuity coefficient? Well, it's not exactly an average effect, right? Because it is applied only locally around that cutoff point. So You should think of it as a weighted average treatment effect, right? Where the weights are the probabilities that someone has of being near the cutoff values. So here are a few examples of commonly used events as regression discontinuity designs. So any law that has a threshold embedded in it, like an income level or an age limit, would make a good candidate for a regression discontinuity design. Geographical boundaries as well can lead to good regression discontinuity designs, where x, your assignment variable, tend to be the distance from the border where something happens, like a change in the law. The same goes for cutoff dates. If an event happened at a given date, x is time and will define the distance from the cutoff date. And then, of course, you focus on observations right before the cutoff date to observations right on the other side of that cutoff date. You should also be aware of what people often call fuzzy regression discontinuity. Fuzzy discontinuity is similar to just strict regression discontinuity or sharp regression discontinuity. It's simply that in this case, D is not precisely determined by X. It's just probabilistically determined by X. So in this case, instead of having D is equal to 0 when X is below this value and 1 when X is above that value, what you have is that you have different probabilities of being treated above and below the cutoff. So let's say the probability of D being equal to 1 is equal to a certain function of x below the cutoff value and a different function of x above the cutoff value. So as you see, the principle is the same, except that you don't really have a clear, sharp determination for your treatment. So in the case of a fuzzy RD, what do? Well, you can just think of that as a instrumental variables design, which is also why I wanted to remind you about the instrumental variables design at the top of this lecture. So the first stage regression would be the one that determines dy based on x, and the second stage regression would include your instrumented di. An excellent resource for more information about regression discontinuity designs is this paper by Lee and Lemieux from 2010 in the Journal of Economic Literature, Regression Discontinuity Designs in Economics. Okay, so we've now made it to the last part of the lecture, which is on propensity score matching. So what's the basic idea here? Well, you have a treatment and it is not randomized. You do not really have a proper control group. However, what you think is that you can find a group of people that are pretty similar to the treated group, and you could use them as the control. And why would you be able to do that? Well, because your treatment might depend on some characteristics. This is not explicitly specified in the design of the treatment, but it might end up being so. And so you could use these characteristics to predict who is likely to be treated and who is likely to end up in the treatment group. So if you find people who have these characteristics, you can imagine that they are like a control group. So let's do a little example just to fix ideas. Imagine you have a land titling program in some villages, but not in other villages. And what you want to know is whether land titling increases ag productivity. So in this case, you're thinking about villages as being treated rather than individuals as being treated. However, the problem is that's not a random treatment, and that is very common. Most programs, such as that one, were not randomly rolled out. So what could you think of that would be a good control group? Well, you would need villages that are similar to those that are treated, but that do not have the program. So the idea is simply to take villages with characteristics that are similar enough to the characteristics of your treated village, but that are not treated, under the assumption that those villages provide a fairly good counterfactual to what would have happened to your villages had they not been treated, and you use them as your control group. So in practice, how does this work? Well, you have data with some treated and some non-treated elements in it, villages or individuals or items, etc. So you have treated and non-treated. Then you compute something you call the propensity score, which is the probability of being treated based on some characteristics. So for instance, you run a probit predicting your treatment status, di as a function of alpha and beta x, where x are your characteristics. And then you take predicted values for everybody in your sample. Those predicted values are the propensity score. Note that both the treated and the non-treated get a propensity score. So even for the items that were treated and that we know that their DI is equal to 1, we still give them a propensity score that is not necessarily 1. It is just the predicted value of their probability of getting D equals 1 given the X's that they have. So once everyone has a propensity score, what do? You match. You try to match treated individuals with untreated individuals that had the same score or a score that was really close enough. And there are many ways to match. You can match by nearest neighbor, you can do kernel matching, etc. We don't need to get into that. The notion is you find control observations that have the same or a similar propensity score as the treated observations. And then once you've decided on these two groups, you can just run regressions the way you would usually do to compute your average treatment on the treated. So you can do a treatment on the treated regression, or you can do a stratified treatment on the treated regression, or you can do a difference in difference regression, etc. There are different ways to treat this data once you've defined a treatment and a control group. An important notion to know about when talking about propensity score matching is that of support. What we call support is the range of p-scores where your groups overlap. So if you line up your propensity scores inside of your entire sample, the treated and the non-treated, of course, most of the treated will have a propensity score that is higher than 0, and some of them will have a propensity score that is very close to 1. They have all the characteristics that predict that they would be participants, that they would be treated. Now, among the non-participants, it's the opposite. You will have non-participants that have a very, very low probability of being in the group because they have the characteristics that tend to not be associated with the treatment. And however, you will have some non-participants that look fairly similar to participants that have all of the characteristics or many of the characteristics that would predict inclusion in the treatment group. So what is called common support is the area between this point, the lowest p-score of a participant, and that point, the highest p-score of a non-participant. Now when you run these specifications, you will use only the part of your sample that is within the common support. So these parts and those parts of your sample get lost. A nice way to visualize this support is actually provided by Stata's pscore2 package. I know that most of the time I like to talk about R, but I particularly like this function in Stata. What do these plots do? They plot the treated sample at the top and the non-treated sample at the bottom. And then they do two histograms, the histogram of the treated sample and the histogram of the non-treated sample. And they are aligned by the value of their p-score. And you can very quickly see how much support you have inside of your data. Here in yellow, you have the treated off support. So these are people that were treated and that have p-scores that were not matched by anybody in the non-treated group. On the other hand, here in blue, you have the proportion of people who are untreated and off support, meaning their propensity scores are so low that they could not be matched to anyone that was treated with such a low propensity score. And here in the middle, the greens and the reds are the ones that are on support. So this is the distribution of the treated observations that have some counterparts in the non-treated group with similar propensity scores. The extent to which you find matches between the two groups tends to depend on the matching algorithm that you're using. So the notion of on support or off support is by no means definitive. It depends on your matching. So there are issues with propensity score matching. It was very popular, maybe at the beginning of the millennium. Now, not so much anymore. There is quite a bit of criticism of the method, and it is not that novel. Now you will note that compared to instrumental variables and regression discontinuity and natural experiments, propensity score matching does not rely on having a clever idea of a good instrument or of a variable or of a design that can help us approximate randomness. Rather, PSM is more of an econometric fix. And so the key assumption that people always bring up about this econometric fix is the assumption of ignorability. So formally, ignorability means the assumption that the potential y's, y having been treated or y having not been treated, are orthogonal to or independent from D conditional on X. So conditional on X, D and the potential outcomes Y are independent. So when would that break down? When is there not ignorability? Well, when there exists an unobserved variable that determines both D and Y. Here's the intuition. Imagine that in reality, D and Y are determined by two things: the X's, which you know about and you're taking care of, and some U that is unobserved. Then you have two individuals that have the same X values, but they have different U. Because they have different U, their D and their Y would be different because U determines them, but you don't know that, it's unobserved. However, because they have the same X, you gave them the same p-score, although you shouldn't have. And so naturally, the estimate will be biased because you will attribute the difference in Y to D rather than to U. So this is very similar to the concept of unobserved confounders. And finally, a few words about how to run a propensity score matching routine in R. Well, there's a great package called Cobalt with functions that do all of this quite nicely. There's one called matchit for matching. There's bal.tab, which does balancing tests. It makes balancing tables. There's bal.plot that also does balancing plots, kind of similar to the one that I showed you from this data output, but it doesn't have these nice color schemes, which I thought were useful for explanations. If you click on this link from the slides, you will get a lot of info about how to use Cobalt to do propensity score matching. And that's it for now. This concludes our lecture. As always, if you have questions, please let me know. I think that at this point I've figured out the best way to get the sound to be relatively crisp and mostly okay. If you think that is not the case, please let me know and I will try to find a different solution. But so far, I think this is good. Thanks again for listening. I really hope this is helpful.